What if we were able to feed a large language model the similarity graph directly? So you can actually see the use case here where you have a query, you then anchor somewhere, and then you move through this graph to figure out essentially the answer based on what information you find. What Llama did is it went from here to here to here to here, and it moved through this graph, and then it actually jumped over to psychology. This is what it was doing. We are getting LLM reasoning, we are getting traversal, and we're getting extraction. So this is what it would look like if you were to have an LLM traverse a similarity graph. Not only was it 0.91, but it never failed a test case. It succeeded in every single test case, and in faithfulness, it had a 1.0 faithfulness across 50 test cases, which is incredibly interesting. Hey, what's going on, everybody? Today, I'm going to be taking you through my year's worth of research into semantic similarity graph traversal algorithms for retrieval augmented generation systems. This is a year's worth in the making. I'm going to give you the full pipeline for how I stumbled across this problem and how I have chosen to solve it. And I really hope that this provides some level of value to you. The purpose of this video is to walk you through the entire pipeline for how I stumbled across this problem, how I chose to attempt to solve it, and I'm going to take you through absolutely everything from beginning to end, and that's the purpose of this video. This video is going to be pretty technical at times, but my goal is that by the end of it, you'll have a pretty good understanding of what the problem is and how I've chosen to tackle trying to solve it. I also want to point out that by no means am I making the case that this is the best solution. This is just one of many, but it's more of a foundational pillar into retrieval augmented generation systems for LLMs and AI models, just because that's the thing I've become passionate about, and I really want to share that research not only with the rest of the world, but I also want to detail how I went about solving these problems so that you guys have a really good understanding for how it may help you in the future. So what we're going to be doing today is we're going to be running through the Jupyter Notebook that is located inside the root of this repository. You're more than welcome to run this with me or on your own. You just got to install the requirements because it is intended to be run locally on a machine. You also are going to have to install Ollama because everything you're going to see here is going to be run through Ollama. There are resources in the project to run this stuff through OpenRouter or through OpenAI or Anthropic or whatever you choose to do, but we're going to be running everything locally, and this is on an M1 MacBook for me. So if you're on Windows, you would have to adapt a couple of the things for that, but other than that, it should all run automatically. So the way that I want to start this off is I want to kind of go back a year to 2024. And back in 2024, there was a network called Bittensor. And you can see it up on the screen right now, most likely, based on how I edit this. Bittensor is a network of machine learning engineers that are essentially coming together to solve problems in a decentralized way. And it's pretty sweet. There are these different subnetworks on Bittensor. And one of them was called chunking. It's now since depreciated, but chunking was one of these different subnetworks. I found a particular interest in the chunking problem. I spent around 4 to 6 months mining on this subnet, trying to solve different problems for the chunking problem. And then in the process of doing this, I slowly sort of moved more into the back end of semantic retrieval augmented generation strategies. And so I got a really, really good, deep understanding of how these systems work and how to optimize them, as well as different strategies for how you can get more and more accurate retrieval. My software engineering background really started with Bittensor. It really started with trying to find high-value problems that companies and organizations and businesses were looking to solve, and just starting with those and learning how to essentially code and write software for these different problems. And so Bittensor was how I actually learned and taught myself Python, taught myself a little bit of Rust and a little bit of Go, so that I would be able to solve some of these problems. And obviously, particularly Python is sort of my mainstay because LLMs are really where I sort of found myself kind of acclimating to. So we're going to go ahead and we're going to get into the actual problem that I've spent over a year trying to solve in various different ways, which is essentially retrieval augmented generation strategies. So what is retrieval augmented generation, or RAG? What is this? The idea is that if you were to ask something like ChatGPT, if you were to ask one of these models, what happens in Harry Potter, the Goblet of Fire, Chapter 6? It doesn't actually know what happens. It may have been trained on that data, so it may be able to guess or infer pretty accurately because of the astronomical corpus of data it's been trained on. But the reality is it doesn't actually have access to Harry Potter, the Goblet of Fire, Chapter 6. It doesn't actually have that information available to it when you ask it. So the goal is, in order to get accurate information from these large language models, we have to feed them that information somehow. Well, how do you feed it Harry Potter and the Goblet of Fire Chapter 6. When you type that into ChatGPT, how do we ensure that the relevant information to answer that question is fed to the AI model so that it can accurately answer your question? And this goes not just in terms of things like, Harry Potter. This can be really important for things like accurate data for research, right? If you're trying to do something like law, like if you have a chatbot that is a law-based chatbot, and you need to make sure that it returns accurate information about the law, that's got to be accurate. You can't have an AI guess for liability reasons, right? And this can apply to medical, all these other different sort of sectors. And so the way that we build these systems is generally pretty much the same, but fine-tuning them for use case is really where the problem sort of branches out into different territories. So I'm going to go ahead and I'm going to take you through the full pipeline for what you would do if you were going to do semantic RAG. You would essentially go to ChatGPT and you would ask it something like, what happens in Harry Potter Chapter 6, okay? Well, the way that this works is specifically for semantic RAG, you have to have access to the data, the factual-based data to answer that question. And the way that we do this is we basically take just a bunch of data, a bunch of text documents, whatever. Let's say Wikipedia, for instance, because we use Wikipedia later. You would use something like Wikipedia, or if it's law, a bunch of law documents. You would take these documents, and what you would do is you would essentially break these documents up, chunk them into different paragraphs based on a variety of different factors, semantic similarity, where the paragraph breaks are, stuff like that. And what you would do is you would take these documents and you would store the semantic meaning of these documents in something called a vector store. So what that means is if you have, let's say, a document about neural networking on Wikipedia, that neural networking document that you have needs to be essentially split up into chunks. The chunks have to be embedded with some kind of semantic meaning, so they mean something in high dimensional space, which we'll get into in a second. And then what you end up doing is you have this vector store that contains the semantic meaning of every single one of those documents, okay? Then when we have this smart retriever, what we do is we use this smart retrieving system that we build through a variety of different frameworks. We build this retriever to match the question to the content in the store. And so if I type in something like Harry Potter Chapter 6, rather than simply just trying to copy the regular expression, instead of just copying the text, what we're doing is we're turning that into a high dimension meaning of something, and then we're looking for that meaning in our vector store, which contains the meaning, essentially, of all of our different documents, okay? Once we have retrieved the information that we believe is the most relevant to answer the query, we then take the prompt the person asked, which is what happens in Harry Potter Chapter 6, along with the text, which would ideally be either Harry Potter Chapter 6 directly or writing about what it would have been about, right? And then we send this to the AI. So we send this to our large language model, Claude, Llama, whatever you send it to. And then what you have is you have the ability now to generate an actual answer, and it's accurate because we have the information that we've retrieved from the back end of these systems, right? And so this is the sort of the thing. Now you might think, okay, this seems pretty straightforward, or at least this doesn't seem like it has a lot of complexity to it, but it actually does, because every single sort of RAG system you build is context and situationally dependent. So it totally depends on what you're trying to do. If you're trying to do something like accounting, where it is not so much semantic, it's all just a bunch of like spreadsheets and tables and databases, that has a very different model than something like law documents or medical journals or vice versa, right? And so it makes a huge difference. I focused on the semantic side of things, and I was focusing more on the chunking side, right? Which we're going to get into in just a second. But I really am hoping that you get a good fundamental understanding for what I'm sort of talking about here. So I'm scrolling a little bit lower in the notebook. And like I said, I am just going to be paraphrasing, but you're more than welcome to actually read. I really just want to kind of walk you through the examples and show you sort of what my thought process was. But I want you to sort of see the way that the chunking subnet was trying to solve this problem, right? Which is essentially, how would you separate Harry Potter, the Goblet of Fire, into paragraphs? It is not as straightforward as you might think, because on a mathematical level, it is not as straightforward as humans, right? If you took the whole entire book and you were to put it into one giant chunk of text and you never separated it anywhere, where is it that you would start to chunk Harry Potter into paragraphs? How do you do this so that they're separate enough that you can have them be stored differently than just one giant block of text? What the chunking subnet was seeking to do is to solve this problem via an API that software developers would essentially contribute to, right? So we would build the API to have essentially world-accurate chunking. And there are currently lots and lots of chunking solutions that already exist. There are tons of libraries you can use. There are different tokenizers that will tokenize the text depending on the situation. There's different text splitters and stuff like that. But the point being made is that my initial sort of approach to this came from the chunking subnet. Now, this is the way that the chunking subnet did their sort of reward structure. So what they did is they used the math that you're going to see here. I'm going to just give you the visualization, but this is directly from the validation code, right? The way that the chunking subnet scored people was essentially through the measurement of the greatest distance between the intra-chunk and inter-chunk similarities. In other words, you wanted to have all of the chunks that were the most dissimilar be as dissimilar as possible, and the chunks that were the most similar be as similar as possible. Additionally, there were constraints sent. So we could not send more than a certain number of chunks. Our chunks had to be under a certain size limit, and we had a certain amount of time to send them back. What they did that was really unique when scoring this way is they turned the chunking problem into a global optimization problem, because every single chunk that you are scoring is scored against every other chunk in the document. So this means that if you have, I don't know, let's say the first or second or third chunk, those chunks are getting compared against like the 20th chunk, the 30th chunk, the 40th chunk. And so this means that it is really important that every chunk is as unique as possible mathematically. And there's a lot of different approaches to sort of solving this problem. I tried things like beam search, I tried dynamic programming, I tried a lot of different things to essentially try to find the ultimate solution to this global optimization problem, and I was really struggling. I tried a lot of different algorithms, and I just was not able to, certainly wasn't the winner on the subnet, but I was really struggling to get absolutely sort of perfect solutions or anywhere close. So what I did one day is I said to myself, the only way that I'm going to be able to approach this from a global optimization perspective is by figuring out if it's even possible to compare every sentence in the document to every other sentence, or vice versa, right? Because if I could do that, if I could just compare every sentence to every other sentence, then I would be able to see which sentences were similar and not similar. And it turns out that not only is that very possible, but there wasn't a ton of research on what would happen if you went about the chunking problem that way. And so that's what I did. So what you're looking at right now is a similarity matrix. This is a NumPy array that contains the cosine similarities between every single sentence in a document. In this case, I actually think it's three sentence sliding windows, and I'll get into sliding windows in just a sec and why they had more success for me in my problem solving that I was doing. But what you're actually looking at is a NumPy array. It's just visualized with matplotlib. And taking an immediate look at it, you can see exactly why I went about solving the problem this way, because you can immediately see the chunks that form inside this matrix, right? So you can see this is a chunk, this is a chunk, this is a chunk. You can see these chunks of sentences that have high similarity to each other, but they also have low similarity to other chunks. So you can see this chunk here is very, very similar. This whole entire sort of paragraph section, this is all inside the neuroscience Wikipedia article. You can see this entire section is absolutely nothing like the rest of it, because you can see how low in similarity it is to all of the sentences that are similar. And so you can see how I was going about the problem where I was saying, oh, this should be a chunk. This should be a chunk. And you can see that this chunk in particular, according to the subnet scoring mechanism, if I were to try to score this against this blue, you can see that would have scored very well, because of the fact that looking at it globally, you have a completely different perspective on the way that you're trying to solve the chunking problem. One thing I really want to add too is that I used sliding windows instead of single sentences. Depending on the situation with my algorithms, when I was doing chunking, I would try single sentence and then I would do sliding windows. Sliding windows add a little bit less granularity. They're a lot more Gaussian. They have a lot more blur between them, and they're a little bit better in terms of what you try to extract out of an embed model. If you try to extract a single sentence out of an embed model, it's a lot different than when you try to extract 3 sentences out of an embed model and then overlap them a little bit. When you have that overlap there, you're able to have a little bit more Gaussian sort of like fade between the two. And that allows you to get 2 sentences and 3 sentences sort of bunched together in a more meaningful way. When you have the just single sentences, it's not bad, but it's a lot more granular, and it doesn't have the effectiveness that I had when I was doing my 3 sentences. You could certainly do this with any, window size. You can do this with 4 or 5 sentence windows. In fact, if you do that in the repository, you can do that in the config YAML. But in my experience, 3 sentence sliding windows was the sort of the sweet spot for me. So it's finally time to run some code. We're going to actually build a similarity matrix here. But before we do that, we want to go ahead and grab some topics that we're going to use throughout the rest of this sort of video and throughout the rest of this notebook. We're going to grab machine learning, psychology, and deep learning as our 3 topics. What it's going to do when I go ahead and start running these is it's going to extract these from Wikipedia. I'll go ahead and pull some of these real quick. So I'm going to start running some of these cells. But what we're going to effectively do here is we are going to pull these Wikipedia documents. And you can see that we've loaded these. We've got some of the configs. These are just configs from the YAML. So we're going to come in here. We're going to go and read these. And you can see we're extracting Wikipedia documents here. And you can see that right now it's pulling these. Right now it's using the LangChain loader. So that's the one I picked. And so when we come down here, you can see these are the articles we picked, and it's pulling all the sentences, it's tokenizing them, it's cleaning them up, and then you can see we now have a corpus we've established for the rest of the notebook. Okay, so now we're at the chunking section. So you can see that we're going to use 3 sentence sliding windows, and you can see chunk 1 is going to be sentence 1, 2, 3, then 2, 3, 4, then 3, 4, 5, and we're going to go through the whole document this way for all 3 of our documents. So if I go ahead and click this, it's going to run it, and you can see we're going to go ahead and do our chunks, and you can see the chunks that we're actually getting for each document. So now we're actually going to go ahead and pull our embeddings, and before I do this, just as a brief overview for those who don't know, what an embed model does is it essentially just encodes semantic meaning into a series of text. And so the way that they're trained is they're trained to understand the difference semantically between different words by putting them in high dimensional space. I've got an image up on the screen from a 3 Blue 1 Brown video. I highly recommend that you check it out if you're sort of new to embed models. But the idea is that we're going to embed these sentences so that these sentences have some level of semantic meaning in high dimensional space so that we can figure out which sentences are close together and which ones are further apart. It's also important to note that when it comes to embed models, every single one of them is different. They're trained with different objectives, different dimensions. The ones that I have done in this repository are high dimensional. So they're using 1024 dimensional, I think it's the MXBAI, essentially the mixed bred AI large model. That one's a 1024 dimensional embedding model. When we were mining on the chunking subnet, we used what was called text embedding Ada 2 from OpenAI. That one is a 1536 dimensional embedding model. So it's a very high dimensional model versus something like Mini LM on Hugging Face. That one's only like 384. MPNet, I believe, is up to 768. And so it just kind of depends on your use case and what you're going for. But we used a very high dimensional model when we were operating on the chunking subnet. So I'm going to go ahead and run our embeddings. So we're going to embed every single one of our sliding windows. We've got 1,475 total chunks. And now what we're going to do is we're going to build our similarity matrices, right? So these are these gigantic NumPy arrays. We're going to go ahead and build one of these for each of our documents. So I'm going to click these. I'm going to go ahead and run through. You can see here's our available documents. We're going to go ahead and run these. And you can see ready to compute similarity matrices. Essentially, this is, like I said, I'm not running you through every inch of the code because you're more than willing to go do that yourself. But you can see here, we've got our similarity matrices created. The shape is always going to be a square because it's every sentence is essentially every window compared to every window. And then you can see the different ranges of similarities, right? Now we want to visualize it. So we're going to do this with Matplotlib. So if I come in here and I go ahead and run this, here's our similarity matrix. This one specifically is for machine learning. So you can see we're choosing the machine learning one right here. So you can see here, this one's pretty similar. You can see there's pretty good similarity between these. There are very few sections that are deeply not the same, that are very much different. But you can see this is sort of what this looks like. And it's all really relative. It's not so much that you're looking for something that's directly low. It's more about the relative similarities. So you can see in this case, just looking here, you can see this is significantly more similar than these sections, right? And so you're really just trying to figure out, okay, which sections are, you can say this is a chunk, let's say this is a chunk, this is sort of a chunk, right? And so that's essentially the purpose of what these similarity matrices are for, but more importantly, this kind of approach to chunking as a whole. If I actually scroll up a little bit here and I go ahead and change this one to deep learning, because I'll just go ahead and do that real quick. If I change this to deep learning, and then I go ahead and run this again, we come down and we run it again, you'll see this one looks significantly different. So you can see this one, this is a very, very different looking chunk. You can see this section right here is definitely what we would consider to be a chunk, right? And obviously I'm more sort of operating at a hierarchical standpoint where ideally, and this was one of the things I had thought about during chunking, is that you kind of have a broader idea, and then within that broader idea, you have sort of sub ideas, right? Like that's effectively how I was going about trying to solve the problem when I had started from this perspective. So this is pretty much the gist of what I had really discovered and sort of the foundational principle behind chunking at the time. This is sort of the main meat and potatoes that I was leaning on when I was really trying to solve a lot of those problems. I built a lot of algorithms that were really designed around things like beam search, like I said, dynamic programming, but I really used this as the sort of primary foundational building block for how to approach the chunking problem, and I had pretty good success after using this. The thing is, I actually went to publish research on using this for chunking. What happened is during the research that I planned to publish, I started asking one really interesting question, which was, is it possible, if we were going to use this as just an example, would it be possible for me to have a large language model essentially anchor somewhere inside a chunk like this, and then just kind of like look around inside here? Is it possible to do this? Now, this is more of a RAG problem rather than a chunking problem. But because we know that this would be considered likely a chunk, or even this or something, or even like this for an example, would it be possible to have a large language model just anchor somewhere in this document and then be able to kind of traverse it a little bit? Is that something that can be done? So during the rabbit hole that I had sort of moved down, I had discovered semantic similarity graphs. You're looking at one right now. And what it effectively is it is and we're going to build one in just a moment, but a semantic similarity graph is every single one of these essentially chunks visualized. They're visualized in 3D, but they're really in significantly higher dimensions. But you're looking at the relationships between all these different chunks in high dimensions. And what I realized is that you would actually be able to traverse through these different documents. And this realization completely changed everything, because up to that point, the way that we had done retrieval augmented generation, rather than trying to traverse through documents, you would just try to do essentially just a similarity match, just a raw grab and go, almost like a claw machine. Whereas what I'm describing is the effect of going onto Wikipedia, clicking an article, and then finding something of relevance inside the article and clicking and going between articles as you're sort of exploring the space between a bunch of different articles. When I found this, and I noticed this revelation, and I noticed that it could be used for retrieval augmented generation, I said, I want to explore that. Because I already had spent so much time looking into these that I understood fundamentally how to build a semantic similarity graph, and I also understood how to make it scalable. So what we're going to go ahead and do now is we're going to build a semantic similarity graph. How are we going to do that? To keep it really straightforward, what we're going to do is we are going to layer these graphs on top of each other like slices of bread, and we're going to attach them sparsely. So instead of actually storing every single one of these computations, right? So this is 378 squared, which we can do quickly in Python. We can calculate this very quickly, but actually storing every single one of these cosine similarity embedding calculations would be really, really mathematically, it'd be a lot of storage. So how do we solve this problem? We do it sparse. We sparse it out. What we do is for every chunk index, we're only going to store like the top 5. And in my case, what I used is top K and top X. Top K being for every document, for every chunk, we're only going to store the top, in this case, 5 similar chunks to that chunk, rather than every single chunk in the document. And top X being cross document, we're also going to only store the top, in this case I use 3, but top 3 similarities to chunks outside this document. And so what you effectively end up with is, in this instance, you end up with what are effectively 3 different documents that are layered like vertical, sort of like layered like this, like slices of bread that are sparsely attached, right? This is the core sort of idea. And what you're effectively able to do with this is you end up with mathematically, it is a extraordinary shrinkage in storage, because you essentially end up with a logarithmic decay in storage value, because as you start getting into the billions of chunks, you're only doing billions of chunks times 5 rather than billions of chunks times billions, right? You end up in a situation where it's actually quite scalable, at maybe perhaps at the cost of accuracy. Depending on what you're trying to do, you can get significantly you can get accuracy depending on how dense you make it. Essentially, these values here determine how dense your semantic similarity graph is going to be. The second thing I want to mention is the actual structure, right? So here is the idea. When we actually build this graph, we're building it with 3-sentence sliding windows, right? So that means that at no point are we ever going to have individual sentences, okay? That's a problem. That becomes a really big issue. And I noticed from an architectural standpoint that we can't not do that. We have to actually have individual sentences somewhere in this knowledge graph, okay? So what I did is I came up with an architecture that allows us to have a hierarchy where you can have sentences, chunks, and thematic elements, essentially theme summaries, thematic elements all stored in a semantic similarity graph in a way where every single node has the sentences listed in it, has its chunk values and its chunk similarities, and then has thematic elements that get extracted. And we're going to do that in just a second. But the point I'm trying to make here is that I essentially architected a particular solution to how are we going to hierarchically store all of the details in this similarity graph. So we're going to go and get into that right now. The goal I had here was to make a lightweight similarity graph where you would be able to traverse it quickly, and the connections that would be stored in it would be the highest quality connections, because if we're only going to store the top 5 for every chunk, then they need to be really high quality connections. You don't want to end up storing really bad connections. You want to maximize the quality of those connections. And so that was the goal here. So we're going to go ahead and we're going to get started. The first thing we need to do is we need to actually extract the themes from our document. There are a number of different ways to do that, but the way that I chose to do it was by taking the first 500 characters of these Wikipedia documents that we have and turn that into essentially one giant paragraph, feed it to Llama, just through OLlama, and then have OLlama provide us with 5 themes per document that we would be able to use to then have be inherited by all of the chunks and all of the sentences in each document. And that's exactly what we're going to go ahead and do now. So when I run this, hopefully I don't lag too much on the screen. When I run this, you will see that OLlama is going to start taking every single one of the themes that we have in each document. It's about machine learning and stuff, but you're going to see it's going to output them. Here they come. It's going to extract the themes, and then those themes are going to be, essentially it's just 5 themes. It's going to take these and extract them. So you can see for machine learning, we have machine learning, artificial intelligence, deep learning. And then with psychology, you can see we have behavior in mind, conscious and unconscious phenomena, stuff like this, okay? What we are going to then do with these themes is they are then going to get inherited to every node inside that document. So that document, when we have a chunk node that's talking about these things, it will have these as themes already extracted. There are absolutely better ways to do this, but this was a lightweight way to do it because, again, we're using Wikipedia documents. If you were doing this potentially with something like law documents or with peer-reviewed research, you could absolutely take an abstract and do this with an abstract. So it's not infeasible, and there's definitely better ways to do it, but this was the way that I extracted themes from every document so that the nodes would be able to inherit theme properties. So it's incredibly, incredibly lightweight and fast. Now, here's the thing. How are we going to bridge the gap between different themes for documents, right? So if we have a chunk that's talking about machine learning, and we have a chunk that's talking about psychology, and we want to connect them at a theme level, not a semantic similarity level, at a theme level, how do we do that? The way that I chose to do this was by taking every single one of these themes that you see here and turning this into an actual sort of essentially a prompt that I would send to an embed model and have an embed model take all 5 of these as one input and output an embedding. And then what you can effectively do is have a semantic similarity comparison between the actual themes in the document. So we'll do that now. So you can see here what we're doing is we're loading embeddings right here. And you can see here what we're going to do is we're actually going to we're going to connect the themes in, we're essentially taking those 5 themes. We are getting the embeddings for just the themes, and then we are extracting the similarities between them. So you can see that's what we're doing here. Now, I've been talking a lot. It's probably time for you to see what I'm talking about. So I'm going to go and run the cell that exports all of this. This is going to come out in the form of a plotly visualization, okay? You will see the full visualization of what this looks like. So you can see here that, and I will probably put it on the screen a little bit cleaner, but what you can see here is the actual theme. You can essentially see all three hierarchies of our similarity graph. So you can see here that if we're looking just from top to bottom, every single node in the graph currently has a theme that is connected to the most similar themes. There's only 3 in this case, but you can see that we've connected the themes for every single node at a similarity value of 0.73. This is cosine similarity. So we're at a 0.7316 cosine similarity. You can see here that at the individual chunk level, you can see every single chunk that's connected to every single chunk. And you can see that here, this is with our top X and our top K. What you're seeing here is every single one of these nodes has 5 connections within the same document and 3 connections to other documents. In this case, we only have 1, but you can see here that every one of these has 5 inside and then 3 outside. Now for sentences, this was pretty complicated because we don't want to have sentences operate at the chunk level. We want to have sentences operate at some kind of deeper level where we don't end up sort of meshing everything together. We want sentences to be accessible, especially if we're going to traverse, but we don't want sentences to pollute the knowledge graph because it would just be sort of untenable. What I chose to do is I put sentences only as children to the parent chunks that they are within. And you can see as an example, if this sentence is in chunks 5 and 6, you can see that it gets inherited by chunks 5 and 6. And this sentence gets inherited by chunks 5, 6, and 7, right? And so what you end up with is you would still have access to the embed data, the embeddings of the individual sentences, because they are cached still. But when we're traversing, we are only going to check for sentences at the level of the chunks that we currently have access to. And so the embedding, we're not comparing sentences to just random chunks. We're only comparing sentences to the chunks that they are already within. Having access to sentences like this is really valuable because later when we start getting into things like early stopping, when we're trying to traverse our similarity graphs, you can actually use individual sentence quality as a metric to say, hey, we extracted one sentence that was so good that we couldn't find anything better in the knowledge graph. Let's just stop. Things like that. So there's a lot of different ways that we can get creative just by having access to sentences without necessarily just traversing at some kind of sentence level. It's important to note that we never actually traverse at the sentence level. We have access to the sentences for things like similarity comparisons, especially for query similarity, but we don't actually traverse at the sentence level at all. We have access to them. It's almost like a claw machine. Imagine we're traversing at the chunk level all the time. We have access to sentences, but we never actually traverse at the sentence level. We're always traversing at the chunk level with access to sentences. Now it's time to go ahead and actually build our semantic similarity graph in 3D, concatenated obviously, but we'll go ahead and run this, right? So we're going to pull this, and this is our graph. So this graph here, what you're currently seeing is all of the 3-sentence windows that we've created. You're seeing the relationships between them. Again, they're concatenated down using PCA. Okay, so these are not absolutely perfect, but they're pretty good. And the values that you can see, they're not measured here because it would just be too much, but every single one of these graph edges that you see here is a cosine similarity comparison in distance. So we have all our distances sort of showing up. And what's interesting, and what you can see immediately, is that psychology is not the same as deep learning and machine learning, but there's overlap. And you can see that if we actually try to move here, you can actually see that there are aspects here where you can see here that deep learning is just kind of all the way, it's very dense. It's very dense in comparison. It's very dense in over here, but you can see that machine learning, while being tangential, has a lot of overlap. You can see that psychology is over here. Psychology doesn't really branch very often. There are bridges, which we'll get into in a second, and you can see that these bridges offer a lot of value, but in reality, if we were going to try retrieval augmented generation, there would be a query in 3D space somewhere, which there will be, and we would essentially just pull the closest things. Maybe we don't want to do that. Maybe instead we actually just want to do something like a local deep researcher, and we want it to be able to traverse this graph, right? There's a ton of different utilities that we can offer if we were able to have an AI move through this graph themselves. And that's exactly what's going to happen. So at this point, we're going to start having a conversation about how we would even solve this problem. We're going to just talk about it like it as though it was just a LeetCode problem, I suppose, right? So here's the deal. How would we go about solving this problem if it was like a Wikipedia journey? If I had a question, if I was interested in something like deep learning, and I wanted to go to Wikipedia and I went on a journey, how would I go about doing this? If we were going to do it algorithmically, it would go something like this. And this is exactly how I went about it, right? So first we would be asking the LLM a question. And then from that point, we have to find somewhere in that graph that we're going to start. And it's not that it doesn't matter where, it actually matters a lot, but we would start somewhere and then from that somewhere begin traversing. Ideally, wherever we start from or anchor to is going to be the most relevant to the user's question. If it isn't, it's going to be really, really hard, especially if we have a very sparse knowledge graph. If we anchor them in the wrong spot, that's going to be a really big problem because we don't want to anchor them in the wrong spot that is not relative to the user's query. At that point, now what we need to figure out is how we're going to start extracting information relative and relevant to the user's query. We do this by traversing. So we're going to move through this knowledge graph one step at a time to figure out what the most important information is. Now, something really important to consider is when do we stop? If we're going to traverse a similarity graph, at what point are we going to conclude that we've retrieved not only sufficient information, but more information is unnecessary to the person's question? At what point do we do that? We need to have some kind of early stopping or just stopping in general figured out to know when are we going to stop. And then obviously once we've done this, we need to figure out a way to get the answer figured out and answered for the user. So we have to return the answer to the user. Now, this is all well and good, but we do need to have a couple of constraints mathematically that we sort of make sure we consider when we're doing this kind of traversal. Number one, everything we need to do needs to be fast. and efficient, because if it's not, if it takes an excessive amount of time, we start asking if it's even worth it when you compare it to something like basic RAG. Again, it's context and sort of use case dependent, but we need what we do to be really, really fast. And we also need to make sure that whatever we do doesn't take up a ton of memory either. Additionally, we need to make sure that what we do is accurate and precise. We'll get into that in a second, but if you've benchmarked RAG systems, you already know that we want to effectively have a high F1 score. I didn't use F1 directly because it wasn't in DeepEval, but having high precision and high accuracy is really important. We want to make sure that we're answering the user's question, but we're answering it accurately and we're not bloating it with too much unnecessary junk, essentially. And then additionally, what we're ideally trying to do here is build something that is more complex, but also more effective than basic RAG, depending on use case, of course. But that was the purpose of the research. Can we do this similarity graph traversal in a way that results in very, very effective prompt answers, essentially? Can we do this more effectively than basic RAG? And after around 3 to 4 months of research, I have landed on a handful of algorithms that have a pretty good effectiveness when it comes to this kind of problem. And they're all available to be used in this repository, and they're obviously what we're going to go over next. Now, in the research, there are 7 that we use. One of them is a basic retrieval algorithm that is effectively what we would be doing for basic RAG. And then there are 6 versions, 6 different retrieval algorithms that are going to traverse our similarity graph rather than doing basic RAG, and we're going to get into every single one of them. So the first one that we're going to talk about is basic retrieval. We're just going to go ahead and do essentially basic RAG, where we're not going to really take full advantage of the semantic similarity graph at all, but we will have access to the sentence layer. We're going to take every chunk node and every sentence node, and we're going to compare every single one of them against the query, just like you would do for basic vector search, right? And then we're just going to pull the most similar stuff. And one of the things that we're considering, as I had mentioned earlier, I want every single one of these algorithms to have a max sentence extraction so that we don't end up just extracting sentences forever. We want to have a point where we actually stop. And for basic retrieval, the 2 ways I did this is just have a max sentence quality. I set it at 10, I think, for every algorithm, just for the purposes of having like a consistency. And when it comes to context grouping later, we'll talk about having 10 I essentially put 10 sentences as the baseline for pretty much everything in this research. But at the point where you have more than 5 sentences that have been extracted, if you have a single sentence that beats other chunks, we just stop. So this means if you have a bunch of chunks that you've extracted and you have a bunch of sentences and then you have a single sentence that is better than grouped chunks, we just extract that single sentence and then all the rest get sort of trimmed and then we stop. So it's effectively just a slightly more complicated version of basic RAG so that you're able to have something that isn't just 9 sentences, 10 sentences every single time. It's a way to kind of have like some little bit of control over that. Now, the first actual traversal algorithm that I'm going to talk about is this one. It's called query traversal. Now, the way that this is going to work is we are going to embed the user's query, and then from there, we're going to find the most similar chunk in the graph to that user's query. Now, that chunk has a bunch of nodes connected to it, right? It has sentences, a couple of them, and it has a bunch of top X and top K chunks that are connected to it, right? So it has a bunch of inter-document chunks that are connected to different documents, about 3 of them, right? And then it has 5 chunks that it's connected to that are in the same document, right? So we're going to look at all of those different chunks, and what we're going to do is we are going to we would have already vectorized it, but we are going to look at which of those chunks are the most similar to the query, not to the current chunk, right? So we're effectively going to look, so here's our anchor chunk. Here are all of the different chunks that are connected to this one based on this one's similarity. And we're going to say, okay, of the chunks connected to our anchor chunk, which one is the most similar to the query? Whatever one is the most similar, we are going to traverse to it and we're going to extract it. Now, there's a couple of stipulations. If there's a chunk that contains a sentence we've already seen, we simply don't extract that sentence, but we can traverse to chunks that contain sentences we've already seen, because remember, we are doing that 3-sentence, essentially sliding window with overlap. So there is a very good likelihood that we would essentially be moving kind of essentially forward and backward in a document a little bit. That's completely fine. We just won't extract a sentence we've already extracted. The second thing is that we will not return to a chunk node that we've already been to, which makes a lot of sense. Now, the last stipulation, and this is really important, is that if we ever see a single sentence that happens to have a higher similarity than any of the other prospective nodes, then we will extract that sentence and stop. The reason we do this is because we're assuming that that single sentence is higher in similarity than the other nodes. And from my experience, this has actually been really, really effective. The reason that this works is kind of weird to explain, but essentially if you have a 3-sentence window, you have a lot more meat that you can actually really sort of get a similarity comparison against. A single sentence doesn't have as much context, and so they tend to score lower in similarity scores. So if you have a single sentence that scores very high, we're assuming that that is a lot more precise and accurate than a 3-sentence window, because a 3-sentence window is polluting the similarity just a little bit. So we can assume that along with the assumption that when we do this, we're going to be in a constant state of descending similarity comparisons. So for instance, our query similarity, our anchor chunk, may be at a cosine similarity value of something like 0.90, like 0.9 basically. And from there, everything below that is going to be 0.85, 83, 81. We're essentially going to be finding decreasingly similar chunks. And the implication is that as we're finding decreasingly similar chunks to the query, which is what we would expect, as that's happening, if we happen to find a very high quality sentence, we are making the assumption that it is high quality in relationship to further traversal into lower similarity chunks. That's the implication. Now, this is a really, really pivotal algorithm to understand, because if you understand this, the rest are going to make a lot more sense. But the point of this is that as we're moving through this knowledge graph, we are looking at the individual prospective chunks that we can jump to, and at every step saying, is this chunk the most similar to the query relative to all the others at this step? And if it is, we jump to it, extract the sentences, and we continue. We do this rather than just doing a claw-like machine, because instead of just doing a claw-like approach with basic RAG, we're essentially jumping in the ball pit and sort of swimming around. And we're saying, okay, as we move through the data, are we going to be able to extract something that is more similar now that we're in the data rather than from a top-down perspective? My mic is bugging on me. I'm sorry. I'm sure you're all laughing as it's like slowly falling. Sorry about that. The next algorithm was experimental. The way this algorithm works is it is as if I went to Wikipedia, and originally I wanted to know what machine learning was. And all I did was just click the most similar link to the current document at every step. So you essentially don't even think about the machine learning part, and you just start clicking, and you just start going through Wikipedia essentially on the definition of a rabbit trail. That's the purpose of this algorithm. Now you might want to know why we would do that. We would do this effectively as a control against the previous algorithm, because we want to know when we're traversing, what happens if we don't consider a query, essentially a query as we're traversing. If we're moving through this semantic similarity graph, and we don't care about what the user asks at all, how far off the beaten path will our algorithm go? How rapidly will it descend into something that has nothing to do with the query similarity, depending on the situation? That was the purpose of this algorithm. Now, while that is the downside, the upside is that it has a significantly greater graph exploration, because what you're effectively doing is you are constantly looking at the most similar essentially similar node to the current node. And so you're in a constant state of looking for the most similar thing as you're moving. Now, one of the problems that I discovered with this algorithm is the fact that when you're actually allowing it to just freely traverse, it's very common for it to effectively just localize in one location and just read up and down. So if, let's say that we're in the machine learning document and we're reading about the history, and that involves maybe 20 sentences. If we're somewhere in there, it is most likely that we're just going to slide up and down the document rather than actually exploring, because the most similar chunk is usually the one either right in front of or right behind the chunk we're looking at, because again, we're doing these sliding windows this whole time. So what we can do to fix this problem is we can say we will not jump to a chunk that contains sentences we've already seen. That's it. The sliding window overlap is effectively nullified. It's mitigated. Even though those chunks are connected, we're not even going to look at them. We're only going to look at the ones that are the most similar, that don't have sentences we've already seen, which is significantly more effective in terms of trying to maximize the exploration, because that's kind of the point. How far would it explore if it didn't have any resemblance to a user query at all? Now, here is how I try to hone the algorithm in, rather than just going completely off the walls. You may remember before that I had said that when we were doing the query traversal, you end up in a situation where the most similar chunk in the graph might be something like 0.9, and then from there, the most similar chunk is like 0.8, 0.8. 79, 78, 77, like that's how that effectively works, which makes sense. The thing with similarity graph comparisons is that because you're not comparing the query similarity at all, you will end up encountering completely different similarity values as you're moving through the graph, because that's just how it's going to happen. And so what you end up doing is you can be at, let's say, a particular chunk here, and then you make a hop based on like a similarity like 0.8, and then 0.7, and then 0.9, and then 0.6. Like this is very common because it's all dependent on a relativistic similarity comparison. It has nothing to do with the query. What I did to hone it in is I said we are only going to allow the algorithm to make hops that have a higher similarity than the previous hop. So what that means is, let's say that we anchor to a chunk at similarity 0.85. We can only then make a hop, whatever our next hop is going to be, we're only going to hop at a similarity greater than that. So a similarity of like 0.86, 0.87, 0.88. We only increase in similarity. And this is effectively creating almost a scorpion tail effect, where these similarity comparisons only get closer and closer and closer. So you end up sort of having like it's like a singularity effect, where as it traverses, the longer it traverses, the more similar the stuff at the end has to be. I absolutely could have taken that off. And if I did that, it would have had a lot, probably worse performance because it would have just gone with whatever. But this was what I did in an attempt to specifically add early stopping. Now we're getting into the complicated ones. Yes, these are the complicated algorithms. The early ones were a lot easier, okay? So this is the thing. You may have noticed with these chicken scratch drawings that I have been creating triangles. When I noticed that I was creating triangles, I was very excited. And from that point, I started going, oh my goodness, what could we do with triangles? There are effectively 3 triangulation algorithms that you can use to do traversal. Effectively, they are doing some kind of geometric triangulation to determine where we should traverse to. And these are a little bit more complicated, but when you see them, you'd be surprised how effective they are. This first one is a little complicated. The idea is that if we have a query here, and we have our anchor, and then we have our chunk candidates, there are similarity comparisons that go from our query to our anchor, from our anchor to our chunk candidate, every single one of them, and then from our chunk candidates to our query. These are all cosine similarities. And what's interesting is that you can actually take those values as essentially they're essentially graph edges, but you can take these values and you can turn them into vertices on a triangle. So you can actually use these as triangle sides. The thought process here was to try to move to chunks for which we would have the highest average similarity across all of the edges that formulate the triangle that chunk is a part of. What that might look like, as an example, you can see here, this is I think this is like 0.74. This is not a to scale, okay, image. But what you can see here is that if you happen to have, let's say that from the query to anchor, you have 0.85. That's pretty realistic, okay? Let's say that you had a chunk candidate, and the chunk candidate had a very, very low similarity here, but it had a very high similarity here, or in this image, a high similarity here and a low similarity here. The idea is that you effectively are averaging those similarities so that you're trying to come up with the best average amongst the triangle, essentially the edges that get created by that triangle. We also create this at every single step. So for every single chunk, we create this. This is essentially a triangle for every single step. Once we take this average is, in this case, it was something like this. You can see that the average here would be 0.775. This would be the average cosine similarity across all 3 of these. And the goal would be whichever one produced the highest average, that would be the chunk we would traverse to. So we're traversing based on a weighted average rather than just based on which one's the most similar. We want to sort of find the highest similarity balance between the query, the anchor chunk, and then the prospective chunks at every step. Now, to me, I think this one's the most mathematically interesting and cool out of all the other algorithms. This one takes what we just talked about and essentially dials it up to 11. So what I was doing before was just taking averages. That's not really being done in geometric space. I'm essentially just taking the cosine similarities and just averaging them. That's not really being done in 3D space or high-dimensional space or anything like this, but this one does. So with this algorithm, what you can see is that instead of actually creating just a random triangle and then averaging the sides, we actually create the triangle and then determine where the center of that triangle is like I said, in geometric space. Once we do this, we figure out where all of the centroids are in every single triangle created by every single perspective node. And then at that point, we say, okay, which one's centroid is the closest to the query? This is the closest thing I could find to finding a meaningful geometric weighted average of the comparisons. And when you compare it to something like what I did previously, like I said, it's effective, surprisingly, but it is not the same thing as actual geometric traversal. This is actual geometric centroid traversal. Now you may notice that this entire algorithm is taking place in 3D. Our embeddings are not in 3D, they are in 1024D. And that is probably confusing, and you'd be right, because this is all being concatenated down into 3D for the purposes of this specific algorithm. And you might ask me, why wouldn't we do it in 1024D? Well, we actually do, because that is the next algorithm. The only difference between this algorithm and the full dim algorithm is the full dim algorithm is running in full embedding space. Whatever model you use, if you want to use a 768, 1024, whatever high dimensional model you're using, it will use the full dimensions of that model rather than using it in 3D. The purpose here is obviously to compare. If we're going to do geometric traversal of any kind, we want to be able to compare the difference between the high dimensional traversal and the 3D traversal. We want to be able to see how they perform. And our last algorithm, and arguably the most exciting one, is the LLM guided traversal. What if we were able to feed a large language model the similarity graph directly without even having to do all this algorithmic traversal? What if we just gave it to a large language model? What would that look like and how would that happen? Now you might be a little bit confused because this kind of goes against semantic RAG as a whole, and it does. This isn't semantic RAG, not in the traditional way. Semantic RAG, like I said, is when you would actually be doing like the whole lookup thing, which is what we're doing. What you would be doing with something like this is very, very different. This would be within the realm of things like model context protocol, like MCP and tool calling. If you were going to go that route, this would be the equivalent. If you've ever talked to Claude or ChatGPT or something, when it does its thinking, and then you see it kind of does something, and then it thinks, and then it does something, and it thinks. This is what it would look like if you were to have this be something it did while it was thinking. To visualize this, I will show you. If I come down here, you can see that this is the prompt that we are giving an AI model. And you can see this is exactly what it says. It says, you are a graph traversal agent. Your goal is to find relevant, essentially, information to answer the content, to answer the query. And you can see here is the question. Here are the sentences that have already been extracted. And here's a summary. And then here are the candidate chunks. And then you are effectively, your task is to figure out which chunk node is the most important. That's it. Not only are you giving it the similarity, but you're also giving it the option to choose if it even wants to take that similarity. And just so you know, this is query similarity. So this is effectively a modified version of the first algorithm I showed you, that query similarity one. This is the query similarity one, but the difference is we're just giving it to a model instead of just doing the full traversal. We just give it to a model and then have the model choose which chunk node we should traverse to next. This is huge because what this would effectively allow you to do, depending on the situation, is if you had a use case where you really, really needed the information to be accurate, you would, instead of just doing RAG at all, this wouldn't even involve RAG. As an example, let's say that you were going to try to talk to a chatbot at bestbuy.com. You open the chatbot and you were talking to it and you were asking it about open box policy. Normal RAG, what it would do is it would try to retrieve text and content about open box policy stuff, like from documents. That's not what this is. This would be the equivalent of effectively having the model have a tool where it goes, let me look at that for you. And then it would say thinking. And what it would do is it would have the ability to tool call this kind of thing. So it could essentially tool call an anchor chunk. It could tool call all of the candidate chunks, and you would build tools for it to manually traverse the similarity graph rather than ever even doing regular RAG. The model would just be able to traverse it itself. And what's even crazier, this can be done very, very lightweight. And so we're going to do that right now. So at this point, we're on to retrieval testing. So this is the part where we're actually going to do a full retrieval using these different algorithms, and we're going to visualize it. You're more than welcome, like I said, to clone this repository, download it, try it out for yourself. But for me, for right now, we're just going to do this one because this is kind of the exciting one. And this one is, it looks very cool when you actually see it in practice, right? And so you're more than welcome to try any of these, but for now, we're going to do this one. Now you can see here, we've already built our similarity graph, right? So all we have to do is it's already in the notebook, right? You can see here's our query, which is, what is psychology behind learning? Do computers learn like humans do? This was a question that I essentially used as sort of the demo for this, right? This way, we're doing a question that involves psychology and computer learning. This is sort of the idea. So we're trying to combine these things, and then we're going to try to visualize this in both 2D and 3D. That's the idea. So I'm going to go ahead and run this. So if I run this real quick, you can see here's our query, and you can see here's the things. This, by the way, is a significantly extended version. So this one you're going to see is not the benchmarking. This is purely for the purpose of visualizing it. So you can see our max sentences is huge. It's 50. The max results is 50. Max hops is 20. So it can hop a ton. This is really designed to just let it go depending on what you're trying to do. So I'm going to go ahead and run this, and we're going to hope that I don't lag too much in the video because Llama is going to be expensive. But you can see here that we're running this. And you can see we're using Llama 3.2. You're welcome to use any model you want. Open router support is available in this repository if you give it a shot. And you can see here that we are getting LLM reasoning, we are getting traversal, and we're getting extraction. So this is what it would look like if you were to have an LLM traverse a similarity graph. This is effectively the replacement for what you would use rather than traditional RAG if that was the approach you were going to take. Again, this is just one example, but you can actually watch it move between the different chunk nodes, which is pretty sick. And you can actually see if I scroll down a bit, you can see this chunk is relevant. This chunk provides relevant information, historical context. You can actually see the reasoning as it's moving through the graph, which is really sick. Now, like I said, this example, it is possible to build a RAG pipeline like this, but it would just be architected very differently. If it was me, I would build tool calling where it was able to effectively do this, where it was effectively able to pull the similarity graph to itself, and then upon pulling it, be able to say, okay, these are the different options and vice versa. And so here at the end, you can see here's the algorithm. You can see it has a score, but the score is not really relevant in this case. And you can see here's our processing time, and then here's our preview of the first 3 retrieved sentences. And you can see why with this algorithm, this is nothing close to RAG speed. This would effectively be an alternative to RAG if you were going to go about it this way. But you can see that these are the preview of our first 3 retrieved sentences. You can absolutely see how this would be really helpful for something like deep research or very specific use cases, but that is the purpose of this one. Now we've retrieved what we need, but we have not answered the question. So we need to answer it. So we're going to generate our answer real quick. And you can see here is our full retrieved content. Here's all the text we grabbed. We grabbed a lot, right? So we're going to feed this into Llama. So if I come up here and I click this, we're going to go ahead and we're going to run it, and it's going to be a second because Llama's getting a giant response. But you can see here's our response once it loads here. So you can see here it said, according to the context, the psychology, is rooted in human cognitive processes and was studied by researchers, blah, blah, blah. It's not directly stated that computers learn exactly like humans do. So you can see that this is essentially our final response. So now that we've done this, let's go ahead and actually visualize this in 2D and 3D, and you're going to really start to hopefully understand the power of what we may be able to accomplish with this, right? So we're going to go ahead and visualize it in 2D and 3D. I personally like the 2D visualizations a little better, but that's just because I came from the chunking problem. So I see it a little bit differently, but 3D is also a really good way to see it too. So if I run this real quick, you can see we're going to build our matplotlib visualization. And you can see this is what it looks like. I cannot tell you what it was like to lay in bed and have this in my head for many, many weeks until I was able to finally get it figured out. And you can see that we're essentially jumping between these different documents all over the place. We're able to store them hierarchically, and we're able to store them in a really organized fashion. But you can see that as we jump based on a variety of different factors. So this way of seeing it globally is awesome, but the problem is we aren't able to really see it at a granular level. So let's go ahead and do that now. If we actually run the next node or the next cell, you can see that at this point you can actually visualize every single individual hop that was made, and you can see at a granular level what's going on, and it's a very interesting story. So you can see that first we anchored to the deep learning document. We then anchored to machine learning after that. We hopped to machine learning, and then we slid up and down this small little sort of section in the machine learning document. Then we hopped to psychology and we slid through it. And then and again, this is an LLM doing this, right? This is Llama that did this. And then you have machine learning, and then you can see that we went and did these little small hops, but you can see the hopping as it sort of went on. You can also see how it hopped from within a particular chunk. So let's go ahead and visualize it now in 3D. You guys saw it through Matplotlib. Let's go ahead and do it in Plotly. So in Plotly, we're going to go ahead and see it, and it's going to go ahead and batch it real quick, and then we're going to zoom this out. And you likely will have already seen this if you've already looked at the rest of the repository. But this right here is a visualization of the same exact thing, but this is it in 3D. If you're interested in messing around with this without even downloading the repository, you can actually download this. It's a release on GitHub. It's just the HTML. I think it's just Plotly visualization or something. But there's an HTML release that you can actually download that contains the HTML code of this exact thing. So right now, while you're watching, you can actually screw around with this right now. So if I come in here to the query, you can actually see our query is in 3D space right here, which is what is the psychology behind learning, right? And where it actually anchored was this point right here. It's kind of hard to see it, but this is point 0. And you can see that the first thing that again, this is the LLM that chose it after getting access to the similarity comparison, right? Such systems learn progressively, improve their ability to do tasks by considering examples. You can see that's actually exactly what it did. And then you can see that what Llama did is it went from here to here to here to here, and it moved through this graph, and then it actually jumped over to psychology. This is what it was doing. So even though we were able to see the matplotlib traversal, seeing it in 3D, you can actually see that what it was doing was finding its way over to the psychology stuff, which is really cool. And then afterwards, it jumped all the way back and eventually sort of found its way in the deep learning section, which is really sick. So you can actually see the use case here where you have a query, you then anchor somewhere, and then you move through this graph to figure out essentially the answer based on what information you find. And like I said, everything you see here, you can rerun using a different algorithm. This is just the Llama algorithm, the LLM one, where it just uses OLlama or OpenRouter or whichever one you pick. But you can absolutely do this with any of the other algorithms, and you can get completely different results. You can change the questions, mess around with it. That's the whole point of this repository. And once it's done, it outputs an HTML for you so that you can actually save it, screw around with it, that kind of stuff. So up to this point, we've shown some really good examples of what can be done. But how do we know if it actually provides any value? Well, we need to benchmark this, or at least have some method in which we can say, okay, is this valuable or is it not? How do we prove its value? Now, there are a ton of different tools for benchmarking, but the problem I was having when I was running into some of the ones that I wanted to use, like Ragas and AutoRag and some of these, was the fact that I needed a significant amount of control over the fundamental areas of retrieval in order to implement some of these different systems. And I went with DeepEval for a particular series of reasons I'm going to get into right now. The first problem I ran into is the fact that I couldn't just use a regular data set, because you can't build a semantic graph out of a data set. It's just not going to happen, not remotely as effectively as using like Wikipedia documents. If I use Hotpot QA or Squad 2, that is not remotely as effective as actually downloading real documents and then chunking those documents and building a graph out of those. That's a lot more effective and a lot more close to a real world use case rather than just using a data set. But what that means is that I'd have to also figure out synthetic question generation that would utilize that graph in a meaningful way. Because if I'm not downloading a data set, how do I essentially build a synthetic data set from a custom similarity graph? How do I do that? The second question is evaluation. I have to have a lot of control over the methods of retrieval, especially if I'm going to do something like the LLM one. I have to have a method in which I can ensure that whatever tool I use is going to work the best for my use case. And so after a ton of research, DeepEval was the one that was the most effective. It's by Confident AI. DeepEval comes with a ton of tools and a ton of wrappers that allow you to build essentially whatever you need for this kind of use case. So I was able to use my own custom semantic graph with their tools to do retrieval and question generation and all that stuff. And I'll get into how that works in just a second. The point I'm trying to make is that DeepEval was absolutely hands down the best solution for this kind of retrieval testing, and the performance I was getting was fine-tuned against DeepEval's essentially evaluation mechanisms. Now, if you've used a tool like Ragas, you know that Ragas supports single and multi-hop context grouping and then question generation. So effectively what they do is they grab similar context based on knowledge graph similarity, I believe. So they have an actual knowledge graph, which has ontologies and stuff like this. Very different architecture. But what they do is they grab similar content and contexts and then generate questions from that. But the thing is, what we're doing here, not only can we go a lot further than just a couple of similar contexts, we can really go quite complex. We can really get some really complicated questions generated because we're already doing similarity graph traversal. So what's to say we couldn't just do similarity graph traversal for our context grouping? Essentially, what if we just flew through the similarity graph to grab contexts that were similar and then generate questions from them? That's what we do. The first one is just intra-document. So all we're doing is we're just grabbing a random chunk in the graph, and then we're looking at the most similar chunk to that chunk that does not contain a sentence we've already seen. What this is doing is this is effectively allowing us to avoid having the overlap issue that we've had, right? But it also allows a little bit of exploration within the same document. So you end up with a bunch of different contexts that are in the same document that might not be directly related, but then can we also retrieve them in that same pathway? That is the goal of that particular algorithm, is just to do it all within the same document. So the next one is theme-based. The theme-based hop is a little complicated, but the idea is that instead of doing any hops inside the same document, every hop we do will be to a different document. But it is not just by semantic similarity. It's actually by theme. What we do is we take a random chunk, and then we only look at the chunks that are connected from different documents. We then rank order the document that it came from, these different chunks, these documents based on theme similarity to the current document. And then we jump to the most similar node by theme, not by semantic similarity. This is big because this means that we are stress testing the system because a thematic hop could actually be more similar than a raw cosine similarity hop. We're essentially doing only interdoc hops. We're only doing them by thematic similarity rather than raw cosine similarity. And then we are depending on the system to traverse based on the cosine similarity. This is really, really valuable and important because what this does is the stress test that's being done is if we are trying to generate context grouping at a theme level, can we traverse at a cosine similarity level despite that? There's other areas too where the stress test is occurring. Not only does it have to hop every single time between documents, and so you can end up with like 3 or 4 or 5 different chunks, contexts that have very little to do with each other. But you can also be in a situation where despite that, if they do, you end up with oscillation because they have to hop every time. So you might have something like machine learning and psychology. And instead of having it hop like once and then this, it's literally oscillating, depending on, like I said, the nature of what gets extracted. But there are situations where you'll end up extracting contexts that just oscillate. So it never ends up doing any kind of reading. It only oscillates or it hops between documents. The third one, and the most important one to take away from this, is the sequential multi-hop. So everything I just said about theme-based, where we're doing all of these different massive hops between documents, and we're never actually doing any kind of intra-document traversal, we're going to throw that on its head. And we're going to say every time we do a theme hop, we are going to read through the document. We're going to slide the window up or down the document and then hop. So if we were in a machine learning document and we hopped to something like psychology, we hop to psychology and then we either move forward or backward in the document based on whichever is the most similar to that particular spot. And then from wherever we land at the end of that reading, we then hop to the next one. So you end up in the situation where you're actually doing theme hops, but you're adding in reading into those theme hops, which makes it a slight bit more complicated. That helps to benchmark the system a lot more than just doing regular theme-based. That's why I both use theme-based and sequential multi-hop for this sort of system. And then the last one is DeepEval native. It's essentially just available to be used, but I didn't really use it. But it's essentially just the basic context grouping that DeepEval does. The DeepEval does have a basic context grouping, but it's essentially just the same thing that you would use for, it just grabs random stuff, essentially. It's not as effective, so it's not really recommended, but it is available, I suppose, if you wanted to give it a shot. Now, the second part we're going to talk about are DeepEval Goldens. So a golden is essentially a full question, answer, context grouping. It's essentially a full entry into what would be our essentially data set that we generate. And the goal is to generate these goldens. Now, here is the deal. DeepEval has a ton of different features that it offers, and I'm going to kind of go over a couple of them. What you can see here, this came directly from the config YAML, but essentially what you see is you can see things like number of goldens is 50. This was for the 50 question data set. You can see filtration. What filtration does is during question generation, what it'll do is after it generates the full question and it's totally done, it'll actually send it to an LLM to say, is this golden good? If it's bad, then don't use it. That's essentially what filtration does. It's not too complicated, but it helps kind of filter out some of the worst stuff. And then the next thing, which is really important, is evolutions. So what an evolution is the first thing that happens when you send these contexts to DeepEval to generate a question. What an evolution does is after it generates a question, it's going to evolve the question by making it a little bit more complicated. So if you ask, like, what is machine learning? Okay, how does machine learning relate to this? Is machine learning related to this other thing? If you wanted to do machine learning this way, you essentially start to evolve the question to make it more and more and more complex. And that's what evolutions do. For my questions, and the default I think is normally 2, but for my questions, what I did is I only used one evolution, and I'll sort of go into the data set in just a second, but the idea is that I only wanted to use one evolution per question because I wanted to still have some kind of level of control. This is where it gets kind of weird, but there are different types of evolutions, and I didn't want to get crazy and just kind of have just the most complex data set possible. I wanted to have some level of control where I was like, okay, we're not going to just do like 3 or 4 evolutions to make the questions untenable. Now, the last thing, just so you know, when we generate the data set, it's going to be generated in a JSON array. But if you want to use this or you want to experiment with any of this stuff, DeepEval normally costs money when you start to try to do evaluations. You do like 10 for free and then you have to pay for it. They allow you to upload data sets using a CSV. And so if you're interested in doing that, these data sets that I had built are actually in the repository. You can just upload them as CSVs. Assuming that you actually use everything exactly the same, that would work because you'd be pulling the same Wikipedia articles essentially. But you can, essentially the idea is that if you configure this properly and you generate a CSV, it'll output a CSV file for you at the end of the data set generation. And then from that point, you can take the CSV and just upload it to DeepEval. If you pay for DeepEval, then you can just put the push to dashboard to true, and then you don't have to upload anything. When it's done with all the goldens, it's just going to push them directly to DeepEval as long as you're logged in on the CLI. So it's just an extra feature just so you're aware. Now, there are 3 data sets that are available for everybody to use. The first one is literally just a dummy one, just to test, just to see if you can essentially have any success with it. I recommend using this just to screw around. But it's just a one-question introdoc hops. It's just a basic hops between. It has reasoning and multi-context evolutions, but it's essentially just to see if you can actually effectively get a full retrieval out of it. The 20-question one was designed to use the theme context grouping, and the models that were used were exclusively GPT-4o Mini for everything. And it was only using reasoning evolution because since the data set is so small, it's sort of like branching it into the different types just didn't make a lot of sense. So essentially just an only reasoning data set that uses the theme context grouping and then GPT-4o Mini as the model for absolutely everything involved. And then the last one is the 50-question data set. So this one is using the sequential multi-hop. It's doing GPT-4o for all the question generation. And then it used reasoning, comparative, and multi-context questions. So that's essentially what this data set is for. And it uses GPT-4o for all the question generation. Now, in terms of retrieval, if you go to do retrieval with a different model, that's fine. But this data set was built with GPT-4o, this one with 4o Mini. These data sets were also filtered and critiqued by using the filtration system I mentioned earlier. So let's go ahead and talk about models. When you're doing this kind of sort of RAG evaluation, we are having models do the actual evaluation and essentially return us different scores. And so there's a ton of different areas in which we can sort of screw around here. And so you have your embedding model. I strongly recommend keeping this the default unless you have a very particular reason to go for a lower model. But you can use essentially any embed model that's on Hugging Face. It's just a Hugging Face model. And then these are the data sets, and you can see the critique model. You can essentially critique with whatever model you choose. And then you can see here that with our DeepEval models, you have question generation, answer generation, and then evaluation, right? And so it's really important to consider what models you want to use. This repository is compatible with OpenRouter and with OpenAI. And so you can see here we're using OpenAI. If you go into the actual config YAML that's in the project, you can see the comments that I've left. But you can use OpenRouter, and so you have a ton of different options. Now, if you use OpenRouter, I do warn against it because with these kinds of evaluations, they are very time-consuming. They can take like hours, and whenever I would hit like 10 questions, it would eventually just kind of time out. And so I don't recommend OpenRouter unless you're doing like really basic testing. Like if you want to test a very specific like OpenRouter model, like Llama, like 80 billion or something, if you have a really specific model you want to test, go for it. You can even do all of this with Ollama if you're really interested, although it might take you 10 years. But you have the options available to do the deep evaluation with whatever models you want to use, which is the whole point of why I chose DeepEval in the first place. So now we're going to talk about the evaluation and what the results were. Now, I've already kind of walked through a lot of this stuff, so I don't really need to rehash it. But these are essentially the parameters that were used for the major benchmark that I had the most success with. And so you can kind of read through these. Like I said, I've gone through a lot of these, but these are essentially how these data sets were generated, so you can see these. And then we're going to go ahead and actually just talk straight up about the results, because these results were really surprising to me. Now, if you've never seen a graph like this, these are essentially the major metrics that are used to benchmark RAG systems. So we would have precision, recall, relevancy, and faithfulness. What precision is measuring is how relevant the actual contexts were in answering the question, whereas recall is measuring if all of the necessary information was retrieved during the retrieval. What this means is that in our case, we are looking to have the highest recall scores we can, and then pushing that up against our precision. Because high recall means that, hey, we had access to this entire similarity graph, and we were able to recall everything that was necessary to answer the question. That's what a high recall score would suggest. Whereas precision says, hey, all the context that you sent was relevant to the question that was answered. One other thing to note is that DeepEval has a system in place where if you score too poorly on an actual test case, it will flag it as a failure versus a pass. And so when you see these test cases, what you're effectively seeing is how many of the test cases did not flag as failures because their metric was too low. And these are all of the averages across the whole data set. So starting off with recall, you can already see here that the query traversal performed pretty well compared to the basic retrieval. The test cases were the same, but you can see the faithfulness was very high. Relevancy was the same. And then you can see the recall was higher. And then the precision was slightly lower. But we would expect the precision to be a little bit different because remember, we're going to be grabbing a lot more information. The purpose of recall is, did we grab all the necessary information? That's where we're essentially looking. And you can see that the LLM guided traversal and the query traversal did absolutely phenomenal in that regard when you compare them to basic retrieval. Now, what's interesting is that you can actually see that the triangulation algorithms did pretty poor on recall, but then their precision was a little bit higher. So you can see that the full dimensional triangulation algorithm that had the centroid, that one performed really well on precision. So it was very, very good at providing relevant information, but it was not good at exploration. So it did not do a good job of really moving around the system as much, right? And again, all of these different algorithms, you have to remember, they have limits on them where they have a max sentence number that they can retrieve. The context generation algorithms are also only retrieving so many sentences. So there's a lot of constraints that are put here that would cause the precision to be a little bit higher potentially than the recall. But you can at least see this as sort of like a baseline. And then when we move to the bigger data set, you see some really interesting results. So you can see that in this case, the recall for basic was 88, but then the recall with query traversal, not only was it 0.91, but it never failed a test case. It succeeded in every single test case. And in faithfulness, it had a 1.0 of faithfulness across 50 test cases, which is incredibly interesting. And additionally, as you can see here, the LLM recall was even higher. So the LLM recall, even though it did fail a test case and the precision wasn't perfect, look at the recall on this one. The recall was staggeringly high when you compare it to the query traversal. It did a phenomenal job of recalling all of the necessary information, even if it didn't necessarily have a perfect relevancy to some of the other stuff that it extracted. It was very good at extracting all of the necessary context. That's the point being made. One other thing I want to mention is that you may recall that the one that actually, the SSG traversal one that actually goes through the semantic similarity graph, this one does not take into account any of the query at all, at any point during the traversal. And so we would expect it to perform lower, and you can see that it did. And this is, like I said, kind of like a good low baseline for saying, hey, we're going to have an algorithm that is going to traverse based on similarity, but it's not going to care one iota about what the query was. And so we would expect this to perform kind of as like a low baseline. And so you can see that it's low baseline, it performing high in precision could just mean the questions were generally relatively easier in this regard. But the recall for sure being sort of like a low baseline is really, really sort of interesting. So you can see that this one performed okay to some degree, but you can it's all essentially relative. So you can see that having this one as at the low end, you can see the guided traversal did a phenomenal job when you compared it. It was a full number of basis points above. And then with the triangulation algorithm, right, you can see that it did a pretty good job. But I think if it was me, the challenge that I was probably running into here was that the triangulation algorithm probably had too many constraints on it. I think that the way that I had architected it prevented it from having a lot more wiggle room in terms of how much it was able to traverse. And so it was constantly taking into consideration the query, but because it was a more averaged approach, I think that caused a lot of limitations on how able to answer the query it was potentially, especially given how much better query traversal just outright ran. I feel like the triangulation has some level of potential, but it would need a lot of fine tuning from other people to really figure out how they could get a maximal use case out of it. But yeah, the absolute main key takeaway is that the 50-50, 100% win rate on the query traversal with the recall that it had is the big sort of key takeaway. And additionally, the LLM guided traversal, where the LLM actually did that move through the graph, it did a phenomenal job at recall. And so that is sort of the main point that I'm trying to sort of make. And the main takeaway being that you can have these LLMs do a phenomenal job moving through these graphs. And if you're constantly moving through them, considering the query at every step, you're going to have a significantly better time doing traversal rather than just doing a basic RAG. So that's everything. That is the entirety of the notebook. And like I said, anybody is willing to clone this and fork it and use it for their use case. Obviously, it's MIT licensed. But I do have a couple of takeaways that I want to sort of leave with everybody, because this is sort of the direction that I expect this kind of thing to go in. There are a ton of things that I just did not have time to explore that other people are absolutely able to do if they take the time. The first one is implementing look ahead, right? I just haven't had time to invest into this too much, but it's absolutely possible to essentially do some kind of beam search where you're able to see all possible moves that would happen 1 or 2 or 3 steps down. Now, that would be very challenging to do at the LLM level. But it is absolutely possible to do algorithmically through some kind of beam search where it's like, okay, we're going to be able to see every possible hop that would happen 2 or 3 ahead. Now, like I said, that would get very complex because you'd be doing some kind of beam search. Absolutely doable, right? So if you implemented some kind of look ahead, that could be a really good place to start. The second thing is the knowledge base, right? So I used a really, really small knowledge base. It just had 10 documents in it, right? It was just, I think, 5 machine learning, 5 artificial intelligence. Scaling this is absolutely possible, but does need to be investigated, right? And so doing this with 500 to 1,000 documents, it's absolutely possible to scale it as long as you keep your semantic similarity graph, as long as you keep your SSG sparse. It's absolutely scalable, but I've not investigated a ton of time into what happens if you do this with, thousands upon thousands of documents, right? Essentially, the goal here was to build the algorithms, stress testing them against that kind of scope. I just don't have the sort of the time to do that, but that's absolutely the sort of one of the next steps that's necessary into doing something like this for production. A third one would be deep research, right? So you can absolutely see how deep research, this could be incredibly valuable if you were to have, everyone that does deep research know that you, depending on the way that you go about it, you can either build sub-agents or you build sub-tasks, right? And then you have these sub-agents do all of the research for you and you do recursive searching, right? It is absolutely feasible to have a similarity graph where you anchor to different locations and have different agents moving through a graph with different objectives. Absolutely possible. And doing a deep research using this kind of technology, absolutely doable. Especially given, like I said, deep research can move at a slightly slower pace. And so you have a lot of options when it comes to the sort of the deep research direction. So I do see a massive sort of opportunity there. But that's the whole point of publishing the research, right? I want to sort of offer this up as a foundational component to moving through these semantic similarity graphs, because I've been doing this for so long. I'm so deep into this stuff that I want to sort of put it back out there to the world and to allow people to start trying to figure this out in a way that is maximally valuable for their use case. One final one would be to actually really go all in on that LLM traversal, right? So I had said before that if you wanted to do LLM traversal, it wouldn't necessarily work in this context because it's too slow. You could absolutely build an MCP tool calling system in which you set up the architecture for a model to be able to call a similarity graph, and then it would be able to traverse it itself and then have full access to it. And so it does the thinking and it moves through the graph on its own while thinking, right? Rather than doing traditional RAG. This is an option depending on what your use case is. But I've been in this space for so long that, like I said, my hope is just that absolutely anybody has gotten any kind of value from this. If you have gotten value from this, I've already seen a couple people fork this thing, which is awesome. I've seen about 8 forks. And so I'm really hoping some other people are going to take this and really try to push it forward and try to really move the technology in a positive direction, right? So I'm absolutely thrilled that if anybody has made it to this far in the video, I guess like it, share it, put it wherever you find it to be the most valuable. I appreciate the time that you spent listening to me rant about this stuff. I've just been drowning in this sort of topic for so long that I wanted to sort of push it out to the world and see what other people are going to do with it. I wish you all the best. Good luck and take care.